given our sequence, and it's a sub n equals 0 to infinity, and what is it defined by? Well, we have this integral n to 2n 2x over x squared plus 1 dx. So essentially, the implication here is that this is your a sub n. And usually when we define sequences, n shows up someplace. And so to be clear, it's showing up in the bounds. All right. Then the limit as n goes to infinity of a sub n is, and we have our choices, log of 1, log of 2, log of 3, log of 4, or log of 5. All right, I suspect a log will be involved in the answer. Okay. Do we have an answer now? What? D. Okay, great answer. That's right. So log of 4. And so what do? Well, we really just need to figure out what does a sub n look like. And it's written in this one form as in terms of an integral. We can say, look, let's just try to figure out what that is in a simpler way, something for us to work with. And so we can integrate 2x over x squared plus 1. That's log of x squared plus 1. We do our evaluation. We have a difference of logs, and so we divide. Now, I don't have any limits in this part because I'm not taking a limit. I'm just trying to understand what the a sub n looks like. So I say, a sub n looks like this log of quantity 4n squared over n squared plus 1. Now, we take the limits. Since we have something easier to work with, we say, well, it's really the limit of this expression. And to understand that, we just say, what's going on the inside? Well, when I look at 4n squared over n squared plus 1, I see essentially polynomial over polynomial, and it's the same degrees. They're both squares. So that tells me, look at the leading coefficients, which are 4 and 1. So it's going to 4 over 1. So our answer is log 4. And all right, good. Now, in some sense, I'll point out, if you were to graph 2x over x squared plus 1, it does look something like the following. And so what's happening is we're looking at the tail. So we're looking from n all the way out to 2n. And we're saying, well, how much area is there? And even though the function is getting close to 0, because we're adding up over bigger and bigger ranges, we're still able to accumulate something. So you might have thought, well, 0, right? Because the function's going to 0, and I'm integrating over places near the end, so I shouldn't get very much. But remember, even if you have very small things, and you add up a bunch of very small things, you can get something non-zero, right? You can get something substantial. And that will be a theme that we'll see in the next few lectures. All right, any questions? All right, well, our thought for the day, an old Chinese proverb. Be not afraid of going slowly, be afraid only of standing still. And I think a lot of times we try to measure our success in some of the wrong ways. It's like, did I get the right grade? I don't like to think about it that way. The question is, am I learning? If I'm learning, the grades will take care of themselves. If I'm not, something is wrong. I need to be moving. I need to be going forward. And I will also say that we're entering into a part of the course which is going to feel less and less familiar as we go on. So it's going to feel extremely different from things that we've seen in Calc 1 and up through this point in Calc 2. And it's going to be frustrating, but keep at it. And just remember, just keep moving forward. Keep doing the best you can. The important thing is that you're growing. You're learning. You'll be okay. You'll be okay. All right. Well, what are our goals for today? We're going to be finishing sequences. And those are our infinite list. And of course, the things we care about are the question's what's happening way at the end. So I have my numbers, maybe A0, A1, A2, da, 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 da. I really care about the da, 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 da. What's happening there? And so that involves limits. And why did I say start sequences? No, we're finishing sequences. We're starting series. I've got to get serious about this. And we're going to talk about what is that? Well, series are things where we're adding up. So it's not just a list. It's like, oh, now add everything on that list together. And of course, how do we add infinitely many things? And we have to understand that. And we'll talk about geometric today. We won't get time for telescoping. That will happen next time. But geometric and telescoping are essentially the two times that we have a good shot of answering the question, what is this infinite sum? Well, up until just before the exam. Just before the exam, we'll have one more shot. Now, in terms of the formula sheet, I will point out that there's this nice little formula here, which gets used quite a lot, and this is related to the geometric sum. And so we'll talk about that little tiny piece, but that's where we're going. All right, we need to finish up from last time. Okay. So this was our slide, and we talked about what's happening. We did our 1 plus x over n to the nth power. That's e to the x. We will see this limit again, and it will show up in certain problems. We talked about x to the n over n factorial. And the moral here is, if you just keep multiplying, the top, you're adding a factor of x, and if you multiply in the bottom, you have things which grow. Since x is fixed, and the thing downstairs is growing, eventually the thing downstairs is going to pass it. And from then on, it's going to be bigger, which is going to cause your whole term to shrink. So that's why this factorial is beating the exponential. And we said at the very last time, we quickly wrote this down. This is about rates of growth. And you want to build some intuition about what is bigger than what. I have two objects. They're racing off to infinity, but which one wins the race? Because that can help inform your decision about how to choose which one to look at, where you should put your efforts. So constants do not get to infinity at all. That's part of their name. They're constants. Logs get to infinity very slowly. They drag their heels, kicking and screaming. Polynomials, they do okay. So these are powers of x. Exponentials, something to the power x factorial. This is not necessarily a complete list, but this is the types of functions we'll see in this class. All right. We kind of waved our hand and said, hey, look at the limit as n goes to infinity of x to the n. And we said, as long as x is small, less than 1, then x to the n goes to 0. Are you convinced about that, or should we talk more about that? So, you're convinced? Okay, all right. It's not too hard to convince yourself. But if I keep multiplying by something which makes me smaller, eventually that's going to force me down to 0. And, all right. This last one, we didn't talk about that, but this is, again, a limit which will show up. Okay. So n to the power 1 over n. If we want to figure out what's happening with this limit, well, we have a challenge. We have an n downstairs. We have an n upstairs. So how do we handle things when there's an n downstairs and upstairs? And in particular, not only is there an n downstairs and upstairs, if you think about what's going on, you have n to the 1 over n, which is going to infinity downstairs and 0 upstairs. Because 1 over n gets small, n gets big. And infinity to the 0 means more work. More work. It's ambiguous, which is to say, it can be almost anything. So we can't decide just by saying, oh, it's infinity to 0. That means it's this. Infinity to 0 means, well, it could be lots of different things. So we have to do more work to figure out what's the right thing. So the question is, how do we do the more work? What tool are we going to use? Sorry, what? Okay, log. Okay, and where are we heading towards? Yes, log is the good answer. Where are we heading towards when we're taking log? Ah, le hôpital, mon ami. Almost always when we have more work with limits, it is le hôpital. Okay, all right, so we're going to call our answer L. So we have L is the limit as n goes to infinity, n to the 1 over n. So we'll take the log of both sides, so that will match. And the nice thing about log is it's a continuous function, which means you can push it into the limit. So this becomes the limit as n goes to infinity of log n to the 1 over n. And why did we do all that? Well, what's a nice property about logs? The powers come down. Yes. Okay, so this becomes our limit as n goes to infinity of log of n, and then times 1 over n, which really means divide by n. Now, in this case, what do we see? Well, this is going to infinity upstairs and infinity downstairs, and that's just right. Just right. It's our more work, but it's the more work version we like. All right, so we apply le hôpital, mon ami. Okay. All right. Now, there is a subtlety here, and we'll pause for a second to say the subtlety out loud. Le hôpital makes sense if we're dealing with continuous functions. Now, here, when we have n, we don't necessarily think of it as a continuous function, but we say, could I replace it by a continuous function? In other words, does log x over x behave nicely, like log n over n? And the answer is yes. Log n over n and log x over x behave nicely. So I can think about it like it were a continuous function. All right. So we take the derivative. And remember, le hôpital, take the derivative upstairs, take the derivative downstairs. What's the derivative upstairs? The derivative of log n. 1 over n. What's the derivative downstairs? 1. And what does this go to as n gets big? 0. Okay, so the answer, n to the 1 over n, is 0, right? No? Okay, why not? Well, because 0 is the log of our answer. So log of what gives us 0? 1. All right. So n to the power 1 over n is 0. Sorry, n to the power 1 over n is 1. Sorry. All right. So there we go. And as a reminder, this sequence is on the formula sheet. This sequence is also on the formula sheet. Or at least these limits are. Any questions? Cool, cool, cool. So, we say a sequence is recursive when the current term we're trying to figure out is computed using previous terms. In other words, I'm looking back and saying, hey, what did I compute just before? Let me take that, modify it a little bit, and here's the current one. So in other words, when I think about the formula that generates the nth term, I see previous terms. Maybe just the one previous, maybe a couple previous terms. So here's a quick example. Suppose we say a0 equals 1. A sub n is n, a sub n minus 1 for n greater than or equal to 1. Find a formula for a sub n. All right, so let's make sure we understand what's going on. So a good thing to do is just start making a list. So here is 1. So I'm going to do it for n equals 1. So now what I'm going to do is everywhere where we see n, we're going to put 1. So a1 is equal to 1 times a sub 1 minus 1, which is a0. But what's a0? 1. So this 1 times 1, which is 1. Now we'll go to the next one. So this is n equals 1. N equals 2. So everywhere where you see in n, replace it with a 2. So a sub 2 is 2. A sub 2 minus 1, a1. But what is a sub 1? 1. So we get 2. All right, we'll try n equals 3. A3. Okay, so everywhere we see n, we put 3. 3, a sub 3 minus 1. So that would be 3, a sub 2. But what is a sub 2? 2. So it's 3 times 2, which is 6. All right. Now we can write some more, but hopefully you get sort of the flow, right? You just, once you have a specific n, you replace that n by the value in all occurrences. So a4 is 4, a3, 6 times 4 is 24, and we can go for a while. So the question, of course, that's the first few terms, but are we picking up a pattern here? Does anything jump out to us? Anyone? Someone noticed the pattern. They've memorized the factorials. All right, good, because I was running out of factorials I hadn't memorized. Okay, it is factorial. Now here's sort of a piece of advice. Sometimes it's to your advantage not to simplify. And I know there's a strong urge. Your high school algebra teachers were like, oh, simplify, simplify, simplify. And so it's in your bones, it's in your DNA. I must always simplify. But if you're trying to find a formula or trying to explain something, sometimes simplifying obfuscates instead of illuminates. So for instance, here we could have written this as, instead of 2a1, we could say, well, it's 2 times 1. And then this 3a2, well, we could have said 3, and a2 is 2 times 1. And then the 4a3, well, it's 4, then a3 is 3 times 2 times 1. And so once you start writing it down without actually multiplying everything together, you say, oh, we're multiplying all the numbers up through n. And so, yes, lo and behold, what do we see? We see that a sub n is n factorial. All right. Now, one other fact, which we are not going to necessarily call on a lot directly, but we rely on it a lot implicitly. We have what's called monotonic. And we've talked about monotonic before. If you think back to Calc 1. Oh, Calc 1, we were so innocent back then. But we talked about monotonic. Do you remember what that was attached to? So it's attached to the first derivative. And we've said monotonically increasing or monotonically decreasing. And so monotonic basically says, I have one behavior. And the behavior says, am I always getting a little bit bigger, or am I always getting a little bit smaller? So monotonic increasing says my sequence is just growing. As I move down my list, as I start walking along the list off towards infinity, every term that comes next is at least as big as the term that came before. Probably a little bit bigger, but at least as big. Monotonically decreasing says, again, I walk off to infinity, but now the terms are getting smaller. Okay. So, what's the nice fact? Well, if a sequence is monotonic, so in other words, it's always going up or always going down, and bounded, which means I can't pass a certain threshold, then it must converge. It has to converge to something. Now, the reason this is nice is because we're going to get into series in just a few minutes, and we are going to be faced with a problem. Most of the time, we will not be able to tell you what the answer is, but we want to be able to say there is an answer. So this is the kind of tool that lets us say, we know there's an answer because we can say it's growing, but it can't grow too big. It's bounded. So this is the kind of tool that lets us say, yes, there is a number. All right, so let's do an example. So we're given that A0 equals 0, and it's a recursive sequence. AN is the square root of A sub n minus 1 plus 2, and it's a convergence sequence. And I'm going to tell you right now it's monotonically increasing. Now, it's not clear why that's true, but I'll justify that pictorially in a minute. So it's increasing. I also claim it's bounded. And I'm going to say, find what it converges to. And I'm sure this is probably bad because that seems like ending a sentence with a preposition, but that's okay. This isn't an English class. Find what it converges to. So I have a recursive sequence. I tell you it converges, and I say, tell me what it converges to. Now, what could we do? Well, we could, of course, start generating data and see what the terms are. But that may not be the easiest thing to do, especially if we don't have a calculator and we don't have lots of time. So we want to be smarter than that. Okay, so how can we approach this? Well, we're told it converges. So we're after the limit L. So that tells me A sub n is approaching L. That's what we have. It's converging. Now I'm going to ask you a question. If A sub n approaches L, what does A sub n minus 1 approach? Is it a trick question? Is it not a trick question? Is it still not a trick question? It's become a trick question. A sub n minus 1 goes to L. Okay, why does that make sense? So what we're doing is we have this long list, right? So we have A0, A1, A2, A3, so forth and so on. And we're looking at this AN. Now the thing is, this number is close to L. What that means is that when I'm in the tail, I'm close to L. But this number right here is right next to A sub n. So if A sub n is close to L for all large n, well, this A sub n minus 1 has also got to be close to L because it's basically right there at the end of the list. It's just one step removed. And everything near the end of the list is close to L. Okay, so what is all this saying? And how in the world can we finish it in this amount of space? Well, whatever the limit is, we have this recurrence. Now let n head off to infinity on both sides. What does the left-hand side approach? So if n goes to infinity, what does A sub n approach? If only we knew the answer to that. Oh, it goes to L, right? We don't know what L is, but we're going to find it. So this left-hand side is going to L. what is this square root of a sub n minus 1 going to do? It's going to go to square root of L. And what does the plus 2 do? It stays plus 2. So here in this step, n is heading off to infinity. So whatever our limit is, it has to satisfy that function. Now the good news is there's no n's. I have an algebraic expression for L. And we just need to solve it. Now, we can solve it or we can guess the answer. Can anybody see what the answer is without us doing a lot of work? Is there a number such that if I take the square root and add 2, I get the number I started with? 4. Now, if you're not happy with that, we can say, well, look, this is the same as square root of L quantity squared, that's my L, minus the square root of L, minus 2 equals 0. And now, if you factor this factors as square root of L minus 2 and square root of L plus 1. So you get that square root of L equals 2, or the square root of L equals negative 1. But which one is impossible? Can square root of L be negative 1? No. Square roots always come out positives out of the square root. So, okay, that's a ridiculous answer. And so, our conclusion is we must have square root of L equals 2, which tells us L equals 4. So there's the limit. Now, we'll do it pictorially. Same sequence. Okay. So I want to think about the following function. F of x equals the square root of x plus 2. And if you were to graph that, that's not the craziest function to graph. It looks like the square root of function, except you shifted it up by 2. Okay, so here's f of x equals square root of x plus 2. Now, to that, I'm going to add the line y equals x. And it'll be clear why I add that line in a second. So let's start with a0. What is a0? 0. So I'm going to mark where my a's are downstairs. So here is a0. Now, how do I find a1? Well, the rule is I take the square root of this value and I add 2. So that's the same as saying come up here and say what's the value of the function? The answer is 2. Now I want to get it downstairs. So how do we do that? Well, if you move across to this line y equals x and were to come down, this would be your a1. So you move up to the curve, square root of x plus 2, across to y equals x, back down, there's your a1. Now how would I get a2? Move up to the curve. That, whatever that value is here, that's your a2. But I want to get it downstairs, so I move across and I go down. There's a2. Now how do I get a3?
Curve from a2.
I go up, across, down. And then what's going to happen is I'm basically going to step, and I'm heading to that intersection. So I'm heading to say, I'm going to be stepping in to where these curves cross. So that curve crosses itself when x equals the square root of x plus 2. Does that look familiar? Or these curves cross each other, I should say. It's the same formula. Now, here, this is the justification for why it's monotonic. Because you see, it's going, every time I plug in, and go across, I end up further to the right downstairs. So it's monotonic. How do I know it's bounded? If I start below 4, I have to stay below 4. So it's bounded by 4. Now, of course, these are very, very simple cases, but this shows you the kind of things that can happen. All right, well, let's do a quick problem. Our last one for sequences. So, given A0 is equal to 17, and A sub n is equal to n minus 18, A sub n minus 1 plus 3, find A sub 20. I want you to try this. Now, I will tell you before you start, you can definitely fit that number on that page. And I'll give you even better news. You can compute this in 2 ways. The bad way, you will not be able to fit it on this page. But don't rush into the problem. Think about this. Think about what's going on, and I think you can see that, aha, there's a quicker way to do it. In case you're wondering, I did ask the AI to do it, and it first did it the horrendously terrible way. So let's beat the AI. Try to beat the AI. When I was asking this question to the AI, it did something which I didn't expect. It started complaining, and it said, do you really want me to keep going? This isn't looking good, after about 10 steps. I said, no, keep going, keep going. And okay, so do we have an answer? Did somebody find an answer to this? 15 is the correct answer. All right. Now, what's the thing? If you're just naive, you can start computing and say, look, I'll get there eventually. But then you can say, well, let me look at what I'm actually dealing with. There's an n minus 18. And you can say, well, I have to go to 20, so I'm definitely going to pass by that. And n minus 18 is nice when n equals 18. Remember, 0 is a friend. We like 0. And so we won't compute the first few terms. We'll skip ahead to A18. Say, okay, what happens with A18? Plug it in. You get 18 minus 18 times A17 plus 3. And you might say, but you don't know A17. We don't have to know. It's going to be some horrifically big number, but no matter what it is, once you multiply it by 0, it's 0. So we can jump ahead. A18 is 3, and then we just plug in the next 2 terms. A19 becomes 6, and A20 becomes 15. All right. So there we go. Our last question about sequences. Well, until the exam, right? Ah, yes. That's coming up. Okay, so continuing on our roadmap that we started. We've talked about sequences, and we say we really care about the end. Great. Now we're coming to the part where we're going to spend a lot of time. Probably about 2 weeks. It's going to be spent talking about series. And series is the plus ... In other words, we're adding up infinitely many terms. So that's the next thing to talk about. Now, the question is, like, how do we do it? But the bigger question is, when does this make sense? All right. So, again, a series, we're adding up infinitely many terms, so we can think of it as it's the sum of a sequence. So now, instead of commas, we put plus signs. And of course, the hard part of adding up infinitely many things is always the end part. The ... What's happening in the tail? What's happening in the last part? So we have to think about that. Now, the challenge is you can't add infinitely many things in finite time. There's just not enough time. So we have to think about, well, how can we justify our answers? And this is an important thing in mathematics. It used to be a wild west a few hundred years ago, and people would just write down all crazy sorts of things. They say things like 1 plus 2 plus 3 plus ... is negative 1/12. And you have to say, what? That's crazy. It doesn't make sense. So we had to say, look, we've got to really figure out what's going on. And so the real question is, what should happen? Now, the way we answer that is we say, well, let's start looking at the beginning. So we'll start adding up the first few terms. So just the first term, A0, the first two terms, A0 plus A1, and the first, in general, n terms, A0 plus A1 plus ... plus AN. Now, those kinds of sums we can definitely do. They're finite. We can add things up. Life is good. So we call these our partial sums. Now we say, all right, the real question is, what's happening to our partial sums? In essence, we form a new sequence. It's a sequence of partial sums. And we say, take the limit as n goes to infinity of these partial sums. If it's a number, then we say the sum converges. And if the sequence of partial sums don't converge, then we say it diverges. And so our real goal for most of the next few weeks is to say, when do things converge? All right. And I will note, on exams, they do sometimes say, find the partial sum of the first few terms. So you want to make sure, partial sum just says, add up to a certain point and then stop. So some comments that we've already made. Finding the exact value of a series, in other words, adding up all the implementing terms, is hard. And so the main question is, does it exist? Does it converge or diverge? That's where we put our energy for most of the next 2 weeks. But there are two special cases. Two special sums that we can talk about now where we can actually add up everything and get answers. There's a third case, but we can't talk about it until we get almost to the third exam. It's like one of the last things we talk about are Taylor series, and which is we get sums coming from functions. But again, that has to wait for quite a while. So for now, there are two things we can find the answers to. We want to talk about them. Today we'll talk about geometric. Next time we'll talk about telescoping. So geometric. The word geometric in this setting doesn't mean necessarily drawing a picture. It just refers to multiplying. So arithmetic, if you've heard that phrase, refers to addition. Geometric refers to multiplying. So if I'm talking about an arithmetic sequence, I'm adding the same amount each time. In a geometric sequence, I'm multiplying by the same amount each time. So a geometric sequence looks like A times R to a power. And what you get is the first term is A, the second term multiplied by R, AR. Now multiply by another R, AR squared. And another R, AR cubed. And so forth and so on. So what's the geometric series? Well, you add those up. A plus A times R plus AR squared plus AR cubed and so forth. All right, so we want to understand what's going on. So here's the justification. We'll walk through it. We start with the partial sum, S sub n. So that says we're starting at A all the way up to A R to the n. Now, if we multiply this by R, what happens is that there's a shift. So A times R becomes AR. AR times R, AR squared. And so forth and so on. And then AR to the n minus 1 multiply becomes AR to the n. And this AR to the n becomes AR to the n plus 1. So there's this shift happening. And now we say, because there's so much overlap, when we subtract, well, we'll get 1 minus R times this nth partial sum is equal to, all these terms cancel except the very first term A and subtract the very last term minus A to the R minus AR to the power n plus 1. So our nth partial sum is very simple to write. Now the great aha. If r is small, what happens to r to the power n plus 1? If r is small, r is less than 1, r to a large power does what? Goes to 0. So the partial sums converge. And so we get the following nice fact. The sum, k equals 0 to infinity, a r to the k, is a over 1 minus r, if the size of r is less than 1. All right. So, the way I remember this is the following. When I'm looking at the sum of a geometric series, I really say, how do I recognize it? I'm looking for a power n. And I care about two things. What's the first term in the series? What do I multiply by at each stage? So the first term, a, that goes in the numerator. Then I divide by 1 minus r, which is what I'm multiplying by at each stage. That goes in the denominator. And then I get my answer. So, for instance, we'll do this 1/2 to the k. This starts as 1 plus 1/2 plus 1/4 2 squared, an 8 2 cubed, 1/16, so forth and so on. What is our first term? 1. So the first term goes upstairs. What are we multiplying by at each stage? 1/2. Right? This, whatever is being raised to a number, that's what you're multiplying by. So 1 minus 1/2. And so, what does this become? 2. So finding the sum of geometric series is as simple as saying, what's the first term? What do you multiply by at each stage? And then life is good. We'll do more practice next time. That's it for today.